You recording now?
Yes.
Okay, good. Well, welcome everybody to Quantum Formalisms. This is part of Quantum Formalism Group Theory Crash Course. This talk is a little bit different than the other lectures in this course, simply because we're going to be doing a lot of hands-on stuff. I'm going to be doing some origami. I'm going to be talking about group theory and a few other things. So some of the notation will be a little different than we use in the class. I will try to point that out. And so let's see if we can get started then. I'd like to thank Ben Borde for letting me speak. He's got the day off. I'm sure he's happy about that. He just checked in a few minutes ago, though. All right, so let's go. I want to talk about origami module design. Now, hopefully my slide deck will move here. There we go. Okay. Up until now in the group theory course, we've basically been learning things very abstractly. In this class, we are going to actually look at some groups you can hold in your hand, which is a little bit different. And we're going to talk about the way they're built, the way they're constructed. And by getting that kind of tacit knowledge, you learn a lot of little details about group theory to come in when you work with the abstractions. So we're going into the concrete here. Much of the material from this talk comes from the field of mineralogy, and which basically mineralogists develop crystallography. Crystallography is basically a great physical example of groups. Crystals are groups. So a lot of the techniques I'm going to talk about have applications in chemistry, metallurgy, material science, condensed matter physics, all kinds of other areas. And it's probably a lot of people. Hey, I'm going to make my slide larger. Is that full page setting? Is that better for everybody? Yay, nay? Okay. All right. So, just to point out here, this little diagram here is a picture of zircon crystals. They're part of a tetrahedral symmetry group. And if you look very closely, it might be hard to read. Each of these faces, like this red face is 0, 0, 1, 1. Those numbers are Miller indices. They're not related to me. I will probably mention 4 different Millers during this course, and none of them, as far as I know, are ancestors. Miller was a mineralogist that did his work in the early 1800s. Wolfgang Kessel. And those indexes basically tell the mineralogist how that face relates to the major group symmetry operators. The major group operators are axes, and basically this tells this mineralogist that this group, this face intersects the x-axis, the 1, 0, 0, which is 1 is the x, 0, 0 does not affect y or z. And that axis is the symmetry axis. In this case, is a twofold symmetry axis. On that crystal, you could do a twofold rotation right here and flip this thing over, and the top will look just like the bottom. But even a lot of people in mineralogy doesn't know that theory relates crystals' faces to groups, elements, which is kind of interesting. Part of the problem was early crystallographers had an issue. The faces were always different sizes. They were in the same position, roughly the same shape, but they moved. The crystal got fatter or thinner or whatever. And so we had the way of handling that. And Miller came up with that system, which we'll talk a little bit about later, but I just wanted to point that out. Oh, both those minerals are from the same symmetry group, by the way. That's both zircons. They're both forms of the crystal it can take, is exactly the same symmetry. Either they look quite different. Okay, so what I do is I start with paper. I make some modulars. I fold that paper into something like an origami modular, something like this. You can see it. I link these things together. In fact, this module was used to make all these shapes. This shape, the first one there, is based on tetrahedral symmetry. If you look, it kind of looks like a tetrahedron. I filled the faces of the tetrahedron with these nice little triangles that were made from these modules. Has exact same symmetry as a tetrahedron. And I use group symmetry when I'm doing it to guide me in terms of picking color selection. So you get some kind of attractive mix of colors. Right? The second one, same module, in what we call the hexoctahedral system, or the cubic system. It's a cube. Third one, same module using the symmetry that you find in a dodecahedron isoctahedron. And if you look, these triangles here are arranged in series of 5, and your dodecahedron's got those. This is 6s, excuse me. My mistake. This is not. This is also a cubic. My mistake. I thought it was another model. Actually, this thing here has the same symmetry as that cube. So when I see these models, I see the symmetry in them so much as the actual more than the faces, and then I try to get to the faces from the symmetry. A lot of people that build geometric stuff work the other way around. They try to put together faces because that's what the result is. I start with the symmetry and then go to build the faces from that. And I'm going to talk about how I do that. Okay. So what is modular origami? Modular origami is the art of taking individual pieces of paper, folding them up into little modules that link together that make attractive shapes or other models. These three are modulars that I created. They're what they collectively call the Miller modules. This is an open indent hexahedron. Makes a great Christmas tree ornament, holiday ornament. This is called a Barry star. This one here uses 6 modules. This is a different modular, uses 6 different modules, but called a Barry star. Actually makes a good Hanukkah decoration. Actually, it was made for a Jewish friend of mine. And this one here is a closed hexahedron module, and it's great for looping together these triangles. And you can make 3D forms or flat patterns. And notice if I put 3 or 4x hex equilateral triangles together, I get another equilateral triangle a little bigger, and that's a useful thing to know. Also, I noticed if I put 6 of these guys together, I get a hexagon, which is kind of nice to know too. And that comes in useful when you're building 3D shapes. Okay, so also these modules typically go together. There's no adhesive, no glue, nothing. They all work by a series of pockets and flaps. And when you get them all together, they lock together and they stay together. So this model here is probably about 15 years old. Looks as good as the day I folded it. This one here is probably about 12. So, all right. So I'm going to fold the Shinobi unit real quick from a piece of paper just to show you guys how it's done. It's hard to do in the air. Can you guys see the whole, George? Can you see the whole paper?
I only see the slides.
Oh, you don't see me?
I see you frozen.
And I'm frozen. Oof. Okay. Okay, you can hear me, obviously.
I can hear you and see the slides.
All right. But I'm frozen. Okay. Well, for a starter, I take 3 of these, what they call Shinobi units. And Shinobi units is a Japanese creator. The units have been around probably 20 or 30 years. They're probably the most famous unit and well-known modular unit in origami. That's why I picked it as an example, because it's something people know. I often give talks on this subject at origami conventions, and there the emphasis is not on math, but on folding, actually creating the models. Here it's going to be about how I use the math to create the models. Okay, put 3D units together, they form these nice pyramids. Got a triangle. This inner triangle is the part that was shown in the model. These pieces here are the flaps. And they go into little pockets. There are little slits right here, and the pockets are right there. They go into them. You can kind of see the pockets on this drawing right there. There's a line, a little pocket right there. You can put them together in 4s, which is nice. Gives you a square footprint. All right. So we put together 3s, we get 3-fold symmetry on this. Not just a nice equal-out triangle, it's 3-fold symmetry. Here we get a square 4-fold symmetry. That's nice to know. It's nice to know when you're dealing with symmetry groups what symmetry you're starting with. The module itself has got 2-fold symmetry. I could put a 2-fold axis right there and rotate it. And if I flip the thing over and rotate, I get exactly the same thing if I rotate 180 degrees. The next thing I do is these modules can be combined into super units. Or, well, I call this a super unit, this triangle. In some of the Japanese literature, that word is translated as subunit, but to me, a subunit is something smaller, and these are something bigger, so I use the word super. I think it's just a translation issue. But Obviously, these triangles put them together. If I put 8 of them together, I get this 8-sided figure made from 8 triangles. It's basically octahedral symmetry. Each of the 4 faces looking down the octahedron. There's one there. It's got a triangle on it. This face has got a triangle on it. That face has got a triangle. And there's 4 faces on the bottom. If I combine 20 of these things, I get something that's based on dodecahedral symmetry or isosahedral symmetry. That's the same symmetry. And dodecahedrons are known for that 5-sided face. In this case, these 5 triangles form that nice 5-sided pentagonal face. They replace the pentagonal faces in the dodecahedron. All right. Just to give you a background. Okay. All right. So for this discussion, I want to talk about symmetry operators. And these are operators that would go into a group, just like a permutation operator. In fact, they're equivalent. You can translate them, but we typically use rotation axis. And in this talk, we'll be using a 2-fold rotation with a little 2-side eye figure here. 3-fold rotation, I'll symbolize that by a triangle. 4-fold square, makes it easy. Another thing that we use is a mirror plane or flip. In 3 dimensions, called a mirror plane. It's a solid plane that goes through an object. Get something here. Straight. I don't know if anybody can see me moving this, but there would be a mirror plane right in the middle of that object there that cuts it in half, and it's the same exact thing on both sides. Just in case you guys can't see me, I'm going to pop back in the slides for a few minutes. This here would be a mirror plane. It goes right through the middle. If this was all the same color, this would be a mirror plane. Looks the same on both sides. Slices right through the object. No mirror plane here. Well, you could. It's a fifth. There's one, but it cuts through here, and then through that triangle. That would be a mirror plane. In 2 dimensions, they're often called lines of inversion, line of reflection, or line of reflection, or a flip. I represent by an M with a dashed line in my diagrams. There is another operator called a center of inversion I'm talking about, where the symmetry takes something on the surface, moves it through the center of the object, and puts it on the opposite end of the surface in reverse. Not real useful for what we talked about today. In some ways, it's a placeholder to keep it honest, because sometimes these inversions are formed just by combining certain symmetry groups. So let's look at these symmetry groups real quick. All right, there you go. So, or symmetry operators that form group. Here's a mirror plane. There's the mirror, which in 2D is a fraud line reflection. It's only a 2D diagram, so we call it either one. We had A and B on this side. We get the mirror image of A and B. Now, sometimes people get confused about what a mirror plane is and what a axis of 2-fold rotation is. They think they're the same. They're not. Here's a 2-fold rotation. That little white dot there means that the axis is going into the paper. I have A and B on this side. When you rotate them 180 degrees, they appear upside down. All right, so you can see there is a difference between these 2 operators. That's why they're mentioned separately. Center of inversion. Center of an object. Call the center of inversion, we abbreviate I. We have an object here on the surface, like A. It gets pushed through that center and comes out back upside down on the other end. Now, a lot of times center inversions are combined with rotation axes. Here's a rectangular or cube-like structure, and it has a 4-fold rotation axis. So it's square on top, and we don't really care if these sides are squared. By this 4-fold rotation, what happens is it rotates quarter of the way to here, and then the inversion operator kicks the A down here and makes it upside down. The next one gets rotated another quarter turn, which would put us here. The upside down A gets kicked through the inversion and produces a regular A. So from the top, it looks like a 180. From the bottom, it looks like a 180 rotation going the other direction. That's the effect of that inversion. Sometimes that's important in 3D geometry, sometimes it's not. It's not going to be real important today, but I want to mention it because that symbol is going to pop up a few times. Combinations. Now, these, just like we combine symmetry, members of a symmetry group, we can say, G1 times G2. These symmetry operators can rotate together. If you took an object and you rotated it, did the first operation and then the second operation, and you look at what you have. Now, in this case, but what happens in nature, in geometry, is that you can't just have any combination. In order for a geometry to be feasible, certain combinations create other symmetry operators. Example, if we have a fourfold rotation and a mirror plane, we try to combine them, we can't have just that. Because when we hit this fourfold against the M1, the moment we make that quarter turn, we've created a second mirror plane, M2. So this does form a group. In math notation shown, it's the dihedral group of order 8. There's always a lot of confusion about the way dihedral groups are labeled. Sometimes called CV4, and in crystallography notation, it's 4mm because it's a fourfold axis and 2 mirror planes. But it's interesting now. This M2 is required to make the thing fit real-life geometry, but it's also required for group closure. That when we have group operators, first operator times the second operator has to give you numbers in the group, which means in order to have this group, you have to have this second operator. And there's a relationship between group closure and where something geometrically is feasible. And it turns out group closure, and you're here, I've never heard anybody say this. Maybe it's in some obscure paper somewhere, but I've never seen it. But group closure is a requirement for geometric feasibility. So when you talk about trying to look at a group and think about it geometrically, remember that closure property, where any two operators have to be your third operators in the group. If you don't have that, the shape, you can't draw the shape, you can't make the shape in 3D, it's just 2D, whatever, it's not geometrically feasible. It might be feasible in some abstract sense, but not in a concrete geometric sense. Okay. Okay, I'm going to see if we have any questions, since I think we've lost George. I'm checking the chat right now. Just, can somebody give me some feedback? Everyone can see me. They can see the slides. They can hear me. I hear I'm frozen. I want to make sure you guys can still hear me, though. Hello, is anyone out there? Oh, great. Let's see. Thank you, Anonymous. I appreciate that. I see George left the stage. Great. Apparently, George can see things when he goes live, when he's off the stage that he couldn't see when he was on stage. Okay. Well, I'm going to expand this then, and I'm glad. Now I can start using this screen, my camera, to demonstrate models to you. Don't know either, Dimitri. Dimitri said he's logged as anonymous, and it's actually Dimitri. I don't know why you're being logged anonymous. We've got a lot of weird things going on today. Okay, so back to full screen. And I will check the chat every now and then for questions. Just post them there, I'll look. If you don't get them right away, it's because I'm yapping. All right, so for the purpose of a 3D geometry group, for what I'm going to do, I'm going to define a symmetry group my way. It may not match any textbook or academic paper definition. It's what I use when I build these things. I have a set X. The set X is all the points in a closed polyhedral surface. In this case, X is this nice square. Could be a tetrahedron, octahedron, weird bizarro shape no one's ever seen or heard of, something totally random with no symmetry. Typically, though, I'm assuming X is a nice closed shape. It's connected. Actually, X is a topological manifold. From those of you who took topology class last year, X is a topological manifold. And these modulars that I fold to cover X to create a polyhedra on top of X, they are basically equivalent charts because they cover the manifold. That's relating this to next class. I realized that last semester taking the topology class. Caduce de Bamborde, that class enlightened me in some things that had nothing to do with the class. G is going to be the symmetry operators, and they will be all your operators. They're going to be the rotations, the reflection, the mirror planes, and the inversions. I'm not worried about other operators like glide planes and twist axis and all those kind of screw axes and those kind of things. Not for the kind of shapes we're going to demonstrate today. That's another set of lectures. And C is the center point of the polynomial. It's not part of the outside set X. It's totally disconnected. All symmetry axis, like this fourfold axis G1, passes through C when it passes through the polynomial. G2, all the G2 passes through C. All symmetry elements cross C. If I had a mirror plane, the mirror plane would cut this guy in half and go right, C would be right in the middle of it, right? C is the center of inversion if you have one. It's that center. So it's important for defining this world, even though we don't actually use it or represent it. It's invariant. No matter what symmetry operator works on, C never changes. Because when I rotate through C, C's on the axis. Every point on that axis is invariant. In fact, the stabilizer, we talked about stabilizer, it's the point right here where the axis crosses into that polyhedral. All right? That's a stabilizer, that little point right there. That's a stabilizer for G2. That's the other stabilizer for G2. It's the 2 points that don't get affected when you use G2. In a mirror plane, a stabilizer would be every place where the mirror plane, say it slashes right through here, comes down and slashes back across the bottom and back up, slashes through that polyhedron. Okay? So hopefully everyone remembers what stabilizers are. It's a set of x's that are not affected by an operator. When the operator hits the x, you return x. In this case, when we rotate a fourfold axis, this point never moves. Neither does this point. Everything else in the space will get rotated. This point just stays the same. And C is the ultimate in stabilizers. It's totally invariant to everything, everywhere. It's not even part of the system. Okay, now, my method for using groups to build origami modules is first is I pick a basic module. And the module I picked, again, was that Shinobi unit, the smaller one. I think it looks better on the camera. All right? So its properties, and we looked at that. It's got twofold symmetry. It can be made into super units, which have threefold symmetry and fourfold symmetry. I can combine the threefold units, super units, into sixes and make a hexahedron, which is sixfold symmetry, which is nice. I can do other things, puts two squares together and make a rectagon, a rectangle if I need to, if I need an elongated face. But the key is I know that that's a symmetry I'm working with. Then I pick a symmetry group which has that symmetry that seems compatible. In this case, 3s and 4s, let's say. I don't even worry about 6s, all right, or anything else, or 2s, 3s and 4s. I use that symmetry group as a model, a map, to fold a polyhedron. I look at the thing's symmetry, and I pick patterns that are kind of go with the symmetry that make it look attractive. And those patterns actually are subgroups. Okay. And then I got a nice model. I got attractive colors. I'm looking pretty. I'm ready to display something. Get some good archive quality paper, fold it up, put it in exhibition somewhere. Next thing happens is now I want to see what else I can do with it. So keeping within the group I've picked, I come up with different polyhedrons. Like here's another one, a smaller version of this. It's also got that tetrahedral symmetry to it. You know, I move my hand here. You can see that's got the nice tetrahedron shape there. You got the four sides. They're all identical. You can kind of see the pattern of that triangle for the tetrahedral face. You look down, you can see the three faces coming together. This object has the same exact symmetry. I basically varied the group of the X in my set a little bit. It's a different X, same G. Notice I got a nice equilateral face, and if I turn it upside down and look through here, I got a nice threefold axis right through the tip, just like the other tetrahedron should have. Same symmetry, different models. And I milked that symmetry group. There's many different models I can come up with by making various changes, using something called a dual, truncating faces, things like that. Changes which preserve the symmetry, and I work within the group. Once I've milked it, then I say, what if I, instead of changing the X in our set, X and G and C, I change G. And I start tweaking the group symmetry element to see what else I can do. So I use some transformations on the group which would change or break the symmetry. And what that does, it moves me into a different symmetry group. Once I've found a new group to play with, what do? I go to the store and I buy some more paper because I've run out of paper. I folded so much stuff out of the first group. I go back to step 2 with the new group and start all over again. And that way I have unlimited material models that like no one else has seen and whatnot. So that's my method. Start for group, fold as much stuff as you can make using that symmetry, tweak the group a little bit, fold some more, tweak the group so much you break it, get a new group, use that to fold, start all over again. The question is, with that method, I really didn't discuss about how I pick the symmetry groups. Like, where do I get these groups from? How do I make them up? Turned out that question has been answered by mineralogists in the 1800s, early 1800s. I showed you this diagram earlier. We talked about this is the Miller indice diagram. Miller was one of those guys. They went and cataloged all possible. They were interested in mineral crystals. They cataloged all possible mineral crystal symmetries possible in 3D. And it turned, the guy that did it, this guy right here, John Frederick Christian Hessel. And in 1830, he spent years working on this, 32 crystal classes. Those crystal classes are the same as our groups, right? To which all crystals must belong. He did this by basically discovered naturally by using geometry that he had available and looking at a lot of rocks. And here's some pictures of minerals here. This is sphalerite. It's got this nice tetrahedral form, those triangles in the tetrahedron. You might recognize that. Love to lump them together. These are quartz crystals, which have a six-sided symmetry. An axis going right through here, and each side's got six sides. Usually you have points if they're perfectly made. And this is a garnet crystal, which has got an isometric, is one of the isometric symmetry classes. And he figured all these out. He spent a lot of time looking at rocks, using a magnifying glass or whatever. Now, some of the groups he came with, that 32, were not, no one ever found minerals that look like that. But he used math to say these minerals, these crystals, these shapes must exist. It's possible they exist. It was like the old days when guys were filling in the periodic table and they said they had a missing element between, two elements. They hypothesized there was an element in there between them. Eventually someone found it. He did exactly the same thing. He hypothesized all these crystal classes. 3/4 of them he found. The other quarter had never been found, but he said they had to exist. They were basically all the possible groups under the conditions in which he was working, the university worked in. And it turned out, and they were not, these classes were not found during his lifetime, the mystery classes. They were still not confirmed. Today, they have been confirmed. He was right. We've proved his hypothesis right. There are minerals out there with all 32 classes. There are crystals, man-made minerals with all 32 classes. It is possible, and no one's come up with any other class other than those 32. Now, part of the problem is those 32 classes are macro things. Crystals are macro items. They're very large. You can see them, you can hold them, whatever. They're based on macroscopic symmetries. And apparently another mineralogist named Bravas that figured out all the various microscopic symmetries that possibly exist when atoms and combine into molecules or crystals. And Hessel used his work to say, based on this microscopic symmetry, it has to fill space. If I fill space with these microscopic symmetry groups, what macroscopic symmetry groups can they make? Which of these symmetries will fill space and make big crystals? That was his requirement to be in that 32 classes. There are some symmetry classes that don't fit in that 32 classes because they cannot be reproduced by filling space with molecules or atoms. All right. Now, interestingly enough, Galois is the guy that coined the word group and is credited with doing it. Hessel did his work at the same time, didn't know anything about Galois, and he developed this entire theory on his own. He is like the co-founder of group theory, but nobody in the math world knows about him. And when you throw in Bravas and Miller and a couple other guys, you've got a very concrete. He created the concrete group theory. Galois created the abstract one, and the two are compatible. They're exactly the same. All right. Now, I want to talk a little about early 1800s doing work on crystallography. Obviously, look at a lot of rocks. You got magnifying glass, maybe a ruler, some kind of caliper to do measurements, measure a few angles or something. A lot different. Today, crystallographers, they've got electron microscopes and X-ray diffraction equipment and computers and all kinds of other fancy things. But in Hessel's day, when he was developing this group theory, high tech looked a little different. There were two inventions. One had been around for a while, but no one had ever figured out how to mass produce it until the early 1800s, about the time Hessel was doing his work. The other invention was invented in the late 1700s. The two together revolutionized work in the math and sciences. They were considered the cutting edge of technology. I'm going to show you what they were. Pencil and an eraser. Here's a quote from Joseph Priestley. He saw an eraser in a store and he loved it. Notes he had to buy it at a specialty shop because couldn't get this at the corner grocery store. And he wrote to people about it. Like, I found this cool thing, right? Erasers were invented in the late 1700s. Pencils were invented 200 years earlier. But the problem is the graphite in the pencil itself was an ore that was useful for military applications, used to cast cannons and things like that. So every time there was a war, the governments of Europe came in and just seized all the graphite from the pencil makers. So pencils were made one at a time. They were handmade if you could get the ore. In the early 1800s, a family called the Thoreaus in the United States was one, figured out a way to start mass producing pencils by using a cheaper grade of graphite ore. They basically mixed graphite with clay. Guy that pioneered it was the author Thoreau's father. That's how the Thoreau family made their money. They were pencil makers. Had one of the first pencil makers in North America. There were also Europeans doing the same thing. So by the time that Hessel was working in his field, pencils and erasers were available, and they were the latest thing. They were the high-tech thing of the day. Things have changed. We got it good today, I think. All right. Well, let's talk about the 32 crystal classes. Problem is there's lots of notation to notate symmetry groups. I primarily use the notation that mineralogists and crystallographers use called the international notation. It's also called the Hermann Magnuson notation. But you can also have show flies, and Coxter had a notation, all kinds of other things. So I just listed the elements. I for inversion, A with a subscript is an axis, M is a mirror plane. The number in front means there's one twofold axis. So I'm going to talk. He broke the groups in these classes into these larger systems, and I'm going to go through them real quickly, system by system. The simplest system he came up with was triclinic. First is petiole. It just has the identity. It's a group that has nothing but the identity, no symmetry whatsoever. I'm called the pinacoidal. Next smallest possible group just has an inversion. You don't see those too often, and when you do, you wouldn't recognize them. They're very unsymmetric. Next system kind of looks like a squash cereal box. If you took a cereal box and you just kind of squash it on the side so the angles were all not 90 degrees, that'd be your monoclitic system. And there were three of those groups. One is just a single twofold axis. Because remember, you don't have a group, you got to have an identity and an inverse for every operator. A twofold axis is an 180-degree rotation. It's its own inverse. So that's all you need, right? Other item is one mirror plane. Again, mirror plane is its own inverse. And also the I is its own inverse. So those are the three groups that have a single item besides the identity, and it's purely because the item they have is its own inverse. The prismatic group, now you get a little fancy. You got a twofold axis of symmetry, which is what this A2 is. The I just comes along as baggage is created by combining these mirror plane and the twofold axis, and a mirror plane. Now this slash here in the international notation indicates the mirror plane is perpendicular to the twofold axis, not parallel to it. Which from this notation you really can't tell that. Right. So in this talk, I'll jump back and forth between these two and occasionally use the show and flies. I'm going to check real quick to see if anybody's got any questions. 3 messages, great. Okay, someone asked about what are charts. They're the modulars themselves, because the charts cover a manifold. And in this case, I'm covering my manifold with these charts, with these modulars, by combining them into threes, fours, whatever, and then covering them. Right? So that's the comments in the chat room here, discussion modules. I can go with my talk then. Right? All right. Real quick, orthorhombic system. This is basically your rectangular box. It's got 90-degree angles, right? And three axes of two full axis symmetry, one on each of the three faces. One goes through each. You have a box, and it's basically going back here. I have a picture of a box here. But that guy there. If these were two full axes, this would be an orthorhombic box. Just each of these faces, the top, the side, and the front, would all have different sizes, rectangles. And so basically you can play around with two full axis mirror planes for the orthorhombic. And these are all groups. Next is the tetragonal system. All these classes are grouped, like I said, are groups. Now you start introducing one axis of fourfold symmetry. So you'd have a rectangular box, but the top of the box might be a square. And so you got your fourfold rotations. And one interesting thing, when I say fourfold rotation here, I'm talking about this A is shorthand for the actual rotations. We don't worry about zero rotation because that's the identity. We already covered that in most cases. But basically, you got 90 degree, in a fourfold, you have 90 degree, 180, 270. You get back to 360, you're back at zero. So there were actually four operators in that group: zero rotation, 90, 180, and 270. Mirror plane is a single operator, but this A4 is a shorthand for four different operators. All right, and you see now we get a fourfold and two folds on the side, which is the box I showed you. You can have a single fourfold mirror planes. That works. It's all closed. It meets all the group properties. And you got all the other notations here. Okay. So these are all things that have like something like a square top. It's in the XY direction, the crystal looks very much the same. The shape looks the same. It's when you go in the Z direction, things get changed a little bit. Next is isometric system. Isometric system basically is like a square. Everything looks the same in every direction. X, Y, and Z, you rotate it, you got basically the same things. And the thing about isometric system, it's characterized by having a threefold axis combined with some other stuff, usually a four, or in this case, a four. In this case, a two. And so what we've got here is we're going to be spending a lot of time looking at, okay, this Gaiordo one is the snub, and we got a tetrahedral here. But the hexaoctahedral, that's a cube. Okay, that is the cube. And I give a talk on origami conventions about what makes a cube, and we spend a lot of time looking at cubic symmetry. And the deal with the cube is it's got the fourfold axis on every face. It's got three full axes on the corner. And then it's got a bunch of two full axes and mirror planes all over the place. And you can see, here's a listing. Here's your three fourfold axes corresponding to each pair of faces. I can get a cube. What am I doing? Grab one here. That's a nice cube. Use this one. Look at a cube here. You got fourfold axis on the face, fourfold axis going through this face, or fourfold axis going through this. You have threefold axes going through each corner. And those are the critical things. And then you got a whole bunch of mirror planes and twofold axes on each edge. I'm going to show you a diagram that we get to we're going to talk more about cubic symmetry. That's where our example is going to be. And there's a hexagonal system. Hexagonal system is basically things are six-sided. Well, actually, there's two halves. There's three-sided things and six-sided things. Trigonal basically means you got a threefold axis, so the thing's a triplet, and then it could be a pyramid or a prism of some kind, and you can have mirror planes and two full axes in the other directions. Very typical. If you throw a 4 in there, you don't have the hexagonal, you're back to isometric. And you'd actually be looking like something like it that fits in isometric. These things are clustered, not because they make sense to cluster, also because mineralogically and crystallography they're the same. The crystals are related. That's why he put them in these different systems. The other half of hexagonal is the hexagonal system. It's all the 6-sided stuff. The key thing here is dominant 6-side axis. Quartz crystal always got 6 sides along its z-axis. And then on the X and Y coming in, you have other symmetry elements. Okay, here. So now we're going to talk about the hexagonal group. Right? And basically, a cube is a representative of this group. And there's a cube, and I've got the axes here. You can see that there's a 4-fold axis going through the front face, the side face, and the top face. This light blue here, the 4-fold axis goes through the top, comes out the bottom. I can rotate the cube this way 4 ways, and it will look the same. People don't realize there's a 3-fold axis on every corner. I can look down the corner of a cube, and it's perfect three-fold symmetry. Okay. And the other axis, I didn't want to make this diagram look too crowded, are the 2-fold axis. And here I've just rotated the cube so this edge is facing me. 2-fold axis there, you can flip the cube over. Every edge of a cube is got a 2-fold axis. In addition, there are mirror planes. And now here's looking down on the corner vertex of a cube, that 3-fold axis. You can see it's nicely 3-folded. But it's also got mirror planes going through it. And every face has got mirror planes going through it. Cube's got mega symmetry, so it's kind of fun to play with that group. And we get way beyond cubes. All right. So I'm going to check for questions again. Anything else? No comments? All right. So I'm assuming everybody's good if I'm not hearing anything. Is that stuff confusing to people? Is it too all over? Please let me know in the chat. Because I can modify this stuff on the fly. I mean, it's not... Okay. So, I'm going to build a cube. I'm going to build a cube 3 different ways, using the symmetry from the group that I know it belongs to. First thing is, I noticed that group's got all those nice 2-fold axes on the edges, right? And the modular has got 2-fold symmetry. So I'm simply going to work with that and concentrate on building a cube using 2-fold symmetry on the edges. And this is the cube I get. Looks good. You can see there's the modulars on the edges, right? So to replicate that symmetry, the 3-fold came when I put 3 modules together. 4-fold comes here when you put the modules together this way. So we're good. That's the same cube I just used as an example. Now I'm going to show you another way to build a cube using the same modules. Again, I'm working. A lot of people build that cube in the origami world and stop. I'm milking symmetry, so I'm going to look at the other symmetry and see if I can find other ways to build this cube. Okay, I got a 4-fold super unit. Cube has got 4-fold axis on each face. So what if I build it from the faces? So I slap each of these guys on the face. Actually, you do 3 of them, because what happens is that this flap will become part of the top face, and this flap will become part of the back face, and whatever. This face here and flap over here will become part of that face. So they kind of share, the faces share flaps. But there, got another cube. We'll pull that guy up. There he is. Okay, nicely built. All the flaps. Okay, now, next step. Excuse me, the colors don't match. I had one set of pictures for units, and then I use other paper for modulars. Okay, now I'm taking that 3-fold modular. Got one around here somewhere. And I'm going to build a cube from the corners out. So in this case, what I'm doing is I'm taking a 3-fold module like this, and notice we got that really nice 3-fold axis going right through the center of that cube. Okay. Okay, and I'm going to, instead of slapping the faces on, I'm going to slap one of these 3 units. I got a 3 unit here on every corner. and build a cube that way by building the 8 corners instead of the 6 faces. Building a little 4, and this is the result. And you can see each of these corners is one of these 3-fold units. Okay. So, and so basically I've used the symmetry within the group 3 different ways to come up with 3 different models of one shape. I showed this model at the convention this year, or variations on it, and people had never seen it. People had been folding for years. I mean, guys from Japan, so nobody had never seen it. So, right? It's at that level. Okay, so next question is, what else can I do with this group, this cubic symmetry group, like the hexaoctahedron symmetry group, with the 4s and 3s and 2s and all the mirror planes? Well, let's remember the definition of group. We have the set X, which is basically the outside polyhedra that the shape is based on. We have G, the symmetry group that operates on that polyhedra. I don't care about C, it's just placed just for to be proper. And so what I'm going to do is find ways to transform X, but keep C the same, or not really worry about the transform. I'm going to find ways to keep G the same, but transform X. And these transformations, there are transformations you can make to a group, the set X that group operates on, that preserves group symmetry. Something you don't think about. We always think about like things we can do to G. Here we're going to do something to X and keep G the same. One is to take the dual. And with a dual, what you do is you basically, every vertex, this is a 3-way vertex, there are 3 faces meeting, swap that out for a triangle, a 3-sided face, in this case equilateral because there's a symmetry axis. Every face, in this case a square, swap out and make it into a 4-sided vertex. So if you swap vertexes and faces, you get a dual, the symmetry is preserved. And I have a little, let me check the thing right now, and I have a video I'd like to play. Okay, I have to actually take my screen, so let me pull it up real quick, the file I need. All right, and I'm going to share my screen now. All right, we'll just do script poly images. Okay, well. And I'm going to click on this little video. And hopefully this video will show us can everybody see my screen? I can't check the chat, but you can see Surface Cube right here. And I'm going to play this video now. And this is a transformation. Every one of these transformations involve truncating or expanding an edge, turning an edge into a face, or a vertex into a face, or a face into a vertex. And they all preserve group symmetry once you see them all. Right? Every one of these shapes has the same exact symmetry. And bingo, there's the dual of the cube, the octahedron. In this case, every one of these 3-fold axes has been switched out with a triangular face. Every square face has been fixed out with a 4-fold vertex. I'm going to run this again. Notice some of these intermediate shapes, because these intermediate shapes also provide templates for models I can create, like that shape right there. I got squares, I got triangles. I can make that. Okay, so that's it for the video. I'm going to put that to bed. Go back to stop my screen sharing. Okay, my slides are back. Okay, wait, looks like I got a few messages here. George says, wow, on the video, and Dimitri says, only see a file. George says a file. Okay. Don't see it. Let me try it again. Sharing my screen. On your screen. Now, you're going to see some really loopy stuff because it's going to like go. I'm running the video again. Can everybody see that? All right, I'm going to repeat what I just said. Start with the square. And bingo, you can see these shapes. That shape right there is a great shape for me to use because it's got triangles and squares in the faces. And the thing will collapse down when you do a swapping to the octahedron. Great. So you guys saw the video now, right? Good. And I'm going back to take my screen off. Hopefully it'll give me back the slides. Great. All right. And a lot of those intermediate shapes, to me, that's let me try to get this going back to slides only. Okay. I'm going to try to pull slides back up again. It was not. Pull this up again. Slides. Okay, good. Got slides back. Great. All right. Apologize for that, guys. I'm going to jump a few pages up. So those intermediate shapes you saw in the video, those are all polyhedra I can mine for new models. And I can tell you I've done every one of them. All right. Okay, we talked about the square, the different shapes of the square. We made our 3 cubes. Now here's the dual. So the octahedron and the cube are duals. Like I said, I replaced every 3 full axis with a triangular face, every square face with a 4-fold vertex, which is also a 4-fold axis. You can see the symmetry elements line up exactly. Actually, I don't have the mirror planes and 2-fold axis on there, but they also line up. It just gets real crowded with those diagrams. So that's how you make a dual, basically by swapping faces and vertices. And then, in true spirit, well, a dual gives me another model I can mine. We've seen this one. This guy right here. That's the octahedron. I've covered every one. I'm going to try to orient there. I've covered every face. Every one of these triangular faces here are one of these little pyramids. It's got 8 faces. There are 8 little pyramids on this shape. It has all the same symmetry as the cube and the octahedron does. There it is. I just showed that. Okay, I just showed the model. One of the intermediate shapes was when you took a cube, and this shape appeared in that video, and you just shave these corners off of the cube down perpendicular to the threefold axis to make triangles. You don't touch the square face, but it kind of eats away a little bit at it. As you shave it, you get this shape, a cuboctahedron. Same exact symmetry. Right? As a cube. And I can create this. I got the squares, I got the triangles. I got all that symmetry elements. I'm cooking with gas here. Oddly enough, if I do that and put these triangles on and the squares, I get back to this, which is a shape I've already made. But I do have a trick. And I'm going to show you another trick to make another shape out of this anyway, which is I can take those triangles, these triangle pieces, and push each corner in instead of having to pop it out. That gives me a nice little model too. And this model, we're going to use an example later. So this is a cuboctahedron. It's just like a cube, except every corner, the point has been pushed in. Okay. All right. Now, using other geometries from that video, those intermediate forms, I created these two models. This one here, the corners got, the threefold corner of the cube got shaved down so much, it became a hexagon. And you can see the faces are still there. There's the square face, there's the square face, but they're much smaller because the hexagon's eaten into them. And if you look, there's a threefold symmetry axis right there because there's one square, rotate, there's another square, there's another square. I have that model in person. It's this one, that one. Which of those is it? It's a hexagon. Okay, there it is. That's this model right here. You can see it. There's your square face. You still have fourfold symmetry on the square face. And then when you go to one of those corner, what would be the corner of the cube? I'm gonna go. Wait a minute. This is this. Yeah, right here. And one of those corners right there. You got that nice hexagonal face, which actually is a threefold symmetry, not a sixfold symmetry. And you can tell because if you put your symmetric axis in there, your symmetry axis, you can see that when you rotate the square this way, it's one square. It's a 1/3 rotation till you get to another square, and another 1/3 rotation when you get to the next one. If it was sixfold axis like a hexagon, you would actually have, like a true hexagon, you would have 6 of those squares, but we only have 3. It's a threefold axis. Another one here, in this case, the edges of the cube got beveled right here into little squares. The triangular corners got kept, and the square face got kept. Same symmetry, threefold axis, fourfold axis, and a twofold axis right there. Both of those have cubic symmetry also, or the hexaoctahedron symmetry. Okay. So basically, from mining this one symmetry group, I was able to develop 6 models. And in reality, there are many more I've actually done. So the question is, what else can I do mining this symmetry group? And also, by doing this, you get a really good tacit knowledge of symmetry, of group, the way group operators work, because you're playing with them all the time, which really helps when we do the group theory homework, because I can visualize some of these things. And Bordy puts an obscure theorem, and I can think of a shape that would illustrate it. Okay, twist fold. Twist folds, a little different. It's a transformation where we're going to take, let's say, a cube. I can use the other cube, the one in the picture. Okay, like this. Taking this cube, and I'm going to twist it along the top axis. When I say 1/8, because when you twist a cube by when you rotate a cube by a quarter, you get back to the same thing. It's a fourfold rotation. I'm going to twist it by half a rotation, half of one of those folds, so 1/8, on the top, and keep the bottom the same. And by doing that, I keep the 2 squares. Now at this point, the edges line up. Top square edge will be here. The bottom square edge will wind up here. And I get a shape that looks like this, right here. It's called a, called nanny prism. And the symmetry's been destroyed. I've kept the fourfold symmetry. Right? Those nice fourfold axes are there. Those threefold axes in the corner, they're gone. A lot of the twofold symmetry axes are gone. Most of the mirror planes have disappeared, and I've only kept 4 mirror planes. And those are the mirror planes that would be on the parallel to the fourfold face, the ones that would be going through this axis here, right with the fourfold. All the mirror planes going this way have been destroyed by that rotation, by that twist. So I've moved now to another group. And if I go way back, see what this other group is. To my group structure. Here we go. One too far. Actually, it's not an isometric. I've got to go back one further than that. The 4 with the mirror planes right here. It's this ditetragonal bipyramidal known as 4MM, also 1A4, and it's a C4V. Got 4 mirror planes and the 1 fourfold axis. That's it. So I've actually jumped groups. I've jumped from this group to that symmetry group. G has changed now and given me a new model. And I could go and start playing with that group, this group here, and see what else I could do with it. Not as much symmetry as the cube, but I could probably get some other stuff out if I tried. All right, just get caught back up again. The next twist is called a snub twist. In this case, we rotate all 3 of the fourfold axes at the same time. They're all half a kilter. The faces still stay. They're not quite lined up now like they used to be. They're kind of at weird angles to each other. But what's happened is these threefold symmetry in the middle, barely visible. It's there, right there. There's a threefold symmetry. You can see because rotate by 3, you should have a cube. You got a cube here on the edge of that. This end's got a cube, or a square, and a square. So you can kind of see this thing would rotate by 3s. But we've lost all this stuff in the middle. We've lost the mirror planes. We've even kept the twofold axis, but they're buried in here somewhere. They're hard to see. But we've lost the mirror planes. And again, we've gone to another group. And that group, that shape is called snub cube. Let's see. Do I have it? I think it's not this one. Right here. This guy right here. That's a snub cube. There's your fourfold axis still intact. If you really look hard, you can kind of see that the threefold axis right here is still intact. You can see the 3 squares, 1, 2, 3, if you were to rotate it. And all this other stuff, those nice edges that were beveled between the cube edges, has all become this gunk. It's all gunked up and we lost a lot of the symmetry in there. But again, makes an interesting model. And there are other variations on the snub twist we can go into, but I don't want to single it. So, okay, good. So that's basically all the model work I wanted to show you. I wanted to talk about one other subject. Often the question is, how many different vertexes can I get in terms of color? Or how many different patterns on the square faces can I get? And it gets us involved in something called symmetry independent configurations. And what those are, what 6 are basically you could, let's say, take a cube and paint one of the faces red. Make this red paper for some reason. Use red modules in there. In fact, I have that right there. You got a nice red face here, and this is a pattern. But it turns out, you'd say, well, there's 6 different ways to do it. There's 6 faces, but not in reality, because if you take into account symmetry, that red face cube, side cube there, if the red face was here, it wouldn't matter to me. It'd be the same cube. I just rotated. You know, if the cube's flipped upside down, it's still the same cube. So take into account all those rotations and flips and mirror planes. The question is, how many configurations do you have? Okay. And that's a real problem. It's actually, there is some current work going in on that right now. So I got some things. And there are 3 theorems that come to mind address those kinds of problems, and they're all group theory based. One is Burnside's lemma, which is the simplest one. The next level of complication is Pauli's enumeration theorem. I put theory as a typo, okay? And another theorem, which is even more complicated and takes into account more cases, called de Bruyn's theorem. Now, figuring out the amount of different combinations is one thing, but they're coming up with some mathematical formula that would tell you what all those configurations, all possible configurations are, has not been cracked. That is a real problem. And in February 2013, this paper here by Mustafa and a bunch of other guys on the use of symmetry and configural analysis for simulation of disordered solids addressed that issue. And that was out of the Journal of Condensed Matter Physics. And basically, he's looking to solve those kinds of problems. How many ways can I paint corners red or blue? For use in understanding the quantum properties of crystalline matter. Oddly enough, what they call disordered solids, I would call crystalline solid. They're calling it disordered because no crystal is perfect, and the imperfections screw up the quantum calculations. And the use of that material is a quantum material. And so understanding how those imperfections affect the quantum properties, the imperfections of the disordered part. They'll ask, given a cube that's got an atom on each corner, how many different ways can I configure an electron spin at those corners, up or down? Let's pick an electron. So we got one electron that's out of place. How many different ways can an up electron appear on those corners? Things like that for their modeling of condensed matter. And they came up with a very primitive algorithm to try to itemize all the possible cases, not just give you the number of them. With the three theorems that we have, just will give you the number. And that's so current error work. I'd love to have that. I'd love to be able to sit down and say, given I've made this really neat looking model here, how many different color patterns can I get? And what are those patterns? And I could pick the ones that would be attractive, and then that's what I would make. So I'm going to look at the simplest cases. We don't have a lot of time for this talk. I don't know how we're doing on time. Before I do that, I'm going to check for questions, which means I got to go to my screen here. Dimitri put a very nice comment about he liked the talk. He combines crystals, origami, and groups. I'd like to thank him for that comment. You still see it on the video. And I was actually talking to somebody last night about I was a little nervous about trying to combine so much different material into one thing. But to give you guys the background, I had to go over all those different subjects. And the history is always interesting. All right, so I'm going to take it and getting back to this. I'm going to look at one example. I'm going to use this guy right here, and I'm going to ask the question, all right, as my example. And I'm going to use Burnside lemma. It's the simplest one. All right, and so we're going to go through it. I'm going to talk about the problem. Okay, here's Burnside's lemma. Let F be a group, let G be a finite group. X/G is the orbits. In other words, what happens is we know from the definition of an orbit that it generates a set. The question is that set will be a whole bunch of G's, GXs. So that set will be a bunch of elements in X. There could be another orbit which contains another set of elements in X that's different. They're different elements. That would be a different orbit. Every set in this is in the same orbit as every other element in that set. Explain that real briefly using this cube. If I just look at vertices, which is what we're going to do, simplify, right? I get 8 of them, one on each corner of the cube. Now, I want to say what's in the orbit of this vertice. Well, I know if I rotate 90 degrees, I get this one. If I rotate another 90 degrees, I get that one. Or I got to go this way, get that one. So all four of these are in the orbit. But on the other side of the coin, with this guy, that particular item, I'm trying to keep it up now. If I bring it, look at this face, and use this axis to rotate through, I get this guy, and this guy. And then if I go to the other face, one of the other faces, I would get all the rest of them. So basically, every vertex is in the orbit of every other vertex. Right? Okay. That's the definition of an orbit. And in some cases where I have more than one kind of point I'm dealing with, I might have a set of orbits for vertex, a set of orbits for center, for squares, whatever, in this configuration where our set X is the entire polyhedra. This is the Cauchy theorem. It's interesting. It relates the fact that it relates the size of the group, number of symmetry operators, the number of orbits, and that example I gave you, the orbit was one. They all fit into one orbit. It's possible there could be some weird configuration where I can't get there using a symmetry operator between 2 points, and then they'd be two different orbits. And the number of stabilizers. And stabilizers are points that are invariant under the symmetry operator. We talked about these a little bit earlier when I talked about fourfold symmetry. I said the place where the fourfold axis enters, that point right there never changes when I rotate with the fourfold symmetry axis. That point's part of the stabilizer. And the point where it comes out on the other side would also be, this side, also be part of the stabilizer. That stabilizer has only 2 points. And so it turns out the number of orbits is equal to the number of stabilizers added up and then divided by the number of symmetry operators. This is a lemma or a byproduct of the orbit stabilizer theorem, which is the theorem I don't know if we're going to cover in this course, but you got Lagrange's theorem, orbit stabilizer, and the thing goes on. And there's a lot of power in that. Now, just a little note about Burnside's lemma. It's also called the Cauchy-Frobenius-Burnside lemma. And it's called the lemma which is not Burnside's. Very unusual name for a lemma. What happened was this lemma, Burnside knew that the lemma was first pointed out by Frobenius. And in his paper, when he wrote his paper and used this lemma, he said, I got this lemma, this is Frobenius's. I got this lemma from Frobenius. He attributed, did the right thing. Burnside's paper was very popular. No one ever read Frobenius's paper. So everyone referred to this lemma as Burnside's lemma, even though Burnside wasn't the creator. Burnside complained. He said, hey, it's not mine. Quit calling it that. It's unfair to Frobenius. So instead, it got renamed. People started calling it the lemma which is not Burnside's. Poor Frobenius can't catch a break. I guess the perfectly correct name for it would be the Cauchy-Frobenius-Burnside lemma, since all three men worked with it and had versions of it. But you see it here. This is the lemma that's not Burnside's. Okay, so now I'm going to look at a specific problem. I got a cube, 8 vertices. Each of these vertices, in this case, are pushed in. They're dimpled in. Right? I have an option when I built this to make it either sticking out or sticking in. How many different ways could I have done that? Which means how many independent symmetry configurations? Because let's say I said, okay, what if I only do it one way? There's 8 of these vertices, 8 different things. No, there's one, because there it is, it's pushed in. And if I flip it over, it's still the same polyhedra. Flip it this way, rotate this way, it's still the same polyhedra. So all those different vertices configurations really count as one configuration when you look at symmetry. The question is, how many of there? What if I try to do 2? I got 1, 2 that's kind of falling apart. I drop it, and the cat was playing with it. But you can see, here's one here, and here's one here. If they're on the same square, they can be anywhere on the cube. But what if I push this one in and push this one in and this one was out? That would be a different configuration because the relationship is different. What if one was on the other side? So I have all these cases I'd have to check to figure out how many configurations there are if I have 2 pushed in. How many configurations are 3? And we keep going. So to answer that question, and it's not the probability theory question, which is all possible configurations not counting symmetry. You would say, well, there's 8 of them, 2 choices. 8 choose 2. Right? But it gives you a number that doesn't take into account symmetry. So we have to take into account symmetry. So it's interesting that this formula does it for us. Now, I'm going to make this problem a little bit easier. We're not going to worry about the mirror planes or inversions. Just worry about the rotations. We got the 3, the 4, and the 2. All right? So we're going to look at a group. This is a symmetry group 2. It works. 3, 4, and 2. And we're going to use Burnside on. And so now I'm going to solve this problem. We have been using up to now the group X, and X being the entire other shell of the polyhedra. I'm going to change it now. Instead, X is going to be all possible configurations of vertices. So if I had a configuration where 1 was in and 7 were out, it would be 1 and in and 7 outs. That's a configuration. In, out, in for 3 of them or something. I mean, so it's a list of every possible configuration, which would be a choose 2 from probability theory, and that's a lot. That's a big set. But of that, how many do we get rid of when we include symmetry in the calculation? I have a typo here. My typo is this should be a C and not an X for the stabilizer because I'm working on the set C now, not the set X. Because I'm only working on the set that contains those 8 vertices. Makes life easier as opposed to an infinite set that just wouldn't work because the thing says it's got to be a finite set. Infinite set of points that make the polyhedra. All right, so okay. And oddly enough, the reason I can use this is each symmetry independent configuration is an orbit. Okay. How many ways can I do 1 vertice? That's 1 orbit. How many ways can I do 2 vertices? There's a couple different orbits there because I don't care about the guys. If I have 1 vertice that's pushed in, or 2 vertices pushed in, and I use G against it, and I rotate it, I still have 2 vertices. To me, that's all one set. They're all in the same orbit. And that is 1 configuration that's symmetry independent. That's an interesting jump, that this idea of symmetry independent configurations are the same as an orbit. Knowing that, you can use Burnside. And again, I have that typo, that should be a C. So in order to do this, I have to figure out every stabilizer for every group operator. If I have to go through G, all these operators, figure out what the stabilizers are, add them up in a sum, divide by the number of items in G, and I get the number of orbits or the number of SICs. If you're not getting this right away, don't feel bad. George and I belong to a group called Math Counts. It's like a math reading club. We read math books, get together once a month. We probably spent 3 3-hour sessions on this stuff, going over it. It gets that hairy. Yeah, and George can attest to that. He can tell you what our group is like. We get very upset. We were supposed to be for an hour or 2, and we always wanted to go in 3 hours. Oh, if anybody would like to ever join that group, let me or George know. We'll give you the information. It's called Math Counts. It's on Meetup. Since we're all meeting virtually anyway. Okay, now, symmetry operators. What does this group symmetry look like? Well, first of all these axes, the 4-fold, the 3-fold, and the 2-fold, have a 0-degree rotation. Well, that 0-degree rotation is the identity. Nothing changes. So at that point, we only list it once as E. right? Okay, now going to the fourfold axis, you have a 90-degree rotation, a 180-degree rotation, or a 270. Once you go 90 degrees past that, you're back to 360, you're back to 0. So these are the only three possibilities. For threefold axis, you got, besides 0, you got 120 and 240. That's it. And for twofold, everything's a 180. Now, so if we take and notice for the fourfold axis, we have three fourfold axes. So number of operators is the number of times this 90 will pop up in that group. It's actually going to be written 3 times, one for each of the rotations, one for each axis. There'll be 3 of them. There are 6 twofold axes, so that 180 will be listed 6 times, 1 time for corresponding and labeled. This corresponds to this particular twofold axis on this edge. And the same with the threefolds. You got 4 vertices, 4 threefold axes. They go through pairs of vertices. So there'll be each 120 rotation is listed 4 times because there were 4 of them, 1 for each axis. I'm just kind of doing some accounting here. Now, number of stabilizers. Well, first of all, no rotation. We got 2 options, in or out, right? Number of potential stabilizers, 2 to the 8th. Each one could be in, out, in, out, in, out. It does not matter. They never change. E doesn't change anything. The second, okay, let's look at the fourfold axis now. If we go to the fourfold axis, right here, and I rotate, well, the stabilizer is that point. That doesn't help me because I'm not worried about that point. I'm worried about the vertices, right? The only way a 90-degree rotation would give me the same thing, right? Let's say in this case, is if all 4 of these were the same. They're either all sticking out or all sticking in. And they're the same color. I'm not worried about color at this point. That would be another theorem. So, all 4 of these guys have to be the same. And all 4 of the ones on the back, if I flip the thing over, would have to be the same. So a number of ways I can get 4 vertices the same and 4 vertices the same. There's only 2 of them. And since there's 2 options, it's 2 to the second. For 180, same issue on the fourfold axis, the 180 rotation. The only way this and this are going to be exactly the same is if the opposite pairs are exactly the same. So this has to be the same as this. These 2 we don't care about because they're kind of like they're not affected, but these 2 have to be the same to make it work. How many ways can I do that? 2 different ways. There are 4 different ways to do it. 2 choices for each way. Since we got in or out, 2 to the 4th. The 270 is identical to 90. It's like a minus 90. So it's 2 to the second. For the threefold axis, how many ways can I rotate this thing so that everything is identical? 1, 2, 3. Don't care about the center one. Center one's not going to change at all. But only way I can do that if I'm doing a 1/3 rotation is if all 3 of these guys are the same. Okay. And there are 4 different ways to do that because they can all be in or out on the front. That's 2 possibilities, and there's in on the back, so it's 2 to the 4th. 240 rotation, same thing. It's basically the same as a minus 120. For the twofold rotations, we got a ton of these. Like, they're all on the edges. They're all right here. Or right here, excuse me. Again, on the twofold, both these pairs have to be the same. The 2 pairs in the back have to be the same, and these guys have to be the same. And it turns out it's also 2 to the 4th possibilities. So those are the number of items in the stabilizer sets for these axes. Add them up, I get 552. Number of operators, add all these numbers up, I get 24. I know that the Burnside theorem says it's the total number of stabilizers, that summation, over the number in G, which is 24, gives me 23 items. So there are 23 different ways I can build this cube where I look at things going in and things going out. Okay, so that's problem solved. Now, I don't have any way of listing. Give me all those configurations. That's an ongoing problem. I solve it for the condensed matter guys do? Well, I'll let them know. If not, I'll see if they put anything out. Okay. And that basically is the wrap up of my talk. And it's been a long time. I'm sure I went over. We covered a lot of material. Real quick back at Burnside. Oh, one other thing I want to mention, these other two theorems, the Cauchy-Frobe, the other two theorems I mentioned, you can look up. There's lots of references on them. I can give you a good one if anyone contacts me on the Discord, the group site. I can give you some other references, papers, and things. The polar enumeration theorem is sometimes called the Polya-Redfield theorem because he had it before Polya did. And de Bruyn's theorem, which was the biggest one and perhaps the most possibilities, is sometimes referred to as de Bruyn's monster theorem. And the reason it's a monster theorem is because it encapsulates all the rest of them. One theorem to rule them all. And it's a homage to another guy named Miller who worked in this field. There was a geometer in the mid-20th century in Cox, there was a grad student named Miller, who came up with a polyhedra that was like breaks all the rules. It's a great counterexample. It's called Miller's monster. And since de Bruyn's theorem is used sometimes on figuring out these polyhedra configurations, de Bruyn's monster theorem was like a kind of a homage to that guy. Another Miller, not related to me. But so I'd mention that. So all these theorems go by multiple names. I'm going to check the chat now. Any questions? Any?
Thank you, Bob.
Okay.
Thank you, Bob. That was amazing.
Great. I'm going to, one more slide I want to put up, I think, which is I want to thank the Quantum Formalism group for letting me do this. Believe it or not, these classes that they offer have been really supportive and really helpful. Helpful to people just learning, but also helpful to people who are doing stuff that need a little more reinforcement. And I think Aaron Bourdet has done a wonderful job teaching these things. I hope his company will let him continue. And I'd just like to thank Quantum Formalism. And I guess with that, we can kill the recording, right? In fact, I'll kill it, I think.